Alright, welcome back everybody. This is the second video from Unit 1, Section 13 of AP Calculus, removing discontinuities. And in this video we're going to look at three more examples of the kinds of problems that you might encounter. If you saw the first video, you should have an idea of what it means to give a formula for the extended function that's continuous at the given point. In essence, our function f of x equals sine of x over x is discontinuous at x equals 0. It has a removable discontinuity, and we want to figure out what that limit has to be in order to fill in the removable discontinuity. So the first thing that I'm going to do when I do this is I'm going to find the limit as x goes to 0 of sine of x over x. And this is one that we should remember. This was one of those limits that we said you got to know this one. If you don't know it, you should know that the limit as x approaches 0 of sine of x over x is equal to 1. We showed that quite a few sections back. And now that gives us all the information that we need to write our extended function that's continuous at the given point. So we're going to write g of x is equal to, and it'll be equal to sine of x over x. Everywhere where x does not equal 0, and it'll be 1 when x does equal 0. And that is a continuous extension of that function, where it is the same graph except it fills in the hole in the graph. And just to show you this real quick, if I were to graph sine of x over x, and if we trace this function and we go over to where x is equal to 0, we see that there is a hole there. Okay, but if we looked at the limit of this as x approaches 0, which we can look at the table, as x approaches 0 from both sides, these values here are getting closer and closer to 1. In fact, they're so close to 1 that they're rounding to 1 for several steps before we get to 0. And so we want to fill in the hole with a value of 1 because that's the value of the limit, and then the limit and the function value are the same, which makes this function continuous. All right, example 5. Let f be the function defined below, where k is a constant. For what value of k is f continuous on its domain? So we have a rational function here and a polynomial function, both of which are always continuous on their domain. So the only place we're really worried about is where x is equal to 5. And so if I take the limit as x approaches 5 of the left-hand branch of this piecewise function, it has to be equal to the limit as x goes to 5 from the right of the right-hand branch of this piecewise function. And so I'm going to go ahead and substitute x in to find these limits, and it gives us this equation: 12 over k cubed plus 5 has to be equal to k squared minus 5. And now I just need to solve this equation. And probably the easiest way for me to do it is going to just be to graph these in my graphing calculator, only instead of x as my variable when I put them in the calculator, I'm going to have k as my variable. So I'm going to go ahead and graph 12 over the quantity x cubed plus 5. And I'm going to graph x squared minus 5. And wherever these two graphs intersect should be the value of k that makes this continuous on its domain, because it's going to make these two pieces equal to one another at that value. And so let's see what happens here. Oh gosh. And so it looks like we've got a value here where they intersect over to the right-hand side of this screen. So I'm going to go ahead and find that 0. no, I don't want a 0. Here, I want an intersection. So I need to choose the intersection command, first curve, second curve. And how your calculator does this varies from calculator model to calculator model, but they're all fairly similar. And we get that this k value is equal to 2.377, where those intersect. And so D is going to be my answer choice. All right, last one. Example 6 from the 2012 AP Calculus AB exam. I believe it was question number 4, maybe, free response number 4 that this comes from. The function f is defined by f of x equals the square root of 25 minus x squared for negative 5 is less than or equal to x is less than or equal to 5. Let g be the function defined by g of x equals f of x for negative 5 to negative 3 inclusive, and x plus 7 for negative 3 exclusive to 5 inclusive. Is g continuous at x equals negative 3? Use the definition of continuity to explain your answer. So when it says use the definition of continuity, that means that we need to, be showing here that the limit and the function value are the same as x approaches 3, and that's how we're going to make our explanation. So the first thing I'm going to do here is I'm going to find g of 3, and I can get g of 3 by just substituting 3 into this function, and I get that g of 3 is equal to 4. Then I'm going to take the limit as x goes to 3 from the left of g of x, and that has to equal the limit as x goes to 3 from the right of g of x. And now here's where I'm going to use the two different branches. I'm sorry, negative 3. We're approaching negative 3. I did all of that at positive 3 when it should all be at negative 3. And I mean, it didn't matter when I was finding g of negative 3. I ended up with the same value, but better get that right value in there. So as x approaches negative 3 from the left, f of x is my function. So that's going to be the 25 minus x squared. And that has to be equal to the limit from the right, which is the right-hand piece. And this limit we actually found when we found the function value, that's 4. And when we put negative 3 in here, again, that's 4. Okay, so limit as x approaches negative 3 of g of x is equal to 4. So, let me just write a concluding statement here. G of x is continuous at x equals negative 3 because g of negative 3 exists. Limit as g approaches, or as x approaches, limit as x approaches negative 3 of g of x exists, and g of negative 3 equals 4 equals limit as x approaches negative 3 of f of x. And so there's my explanation from the definition of continuity in my 3-step test for continuity. All right, that's going to be the end of this video. See you next time when we get into section 14 of Unit 1. We're getting very close to the end of Unit 1 here. Not much left. So we'll see you next time, and have a great rest of your day.